Okay, I'm going to go ahead and get us started so that the speakers have time. So this is the session previews for tomorrow morning's sessions, which will be at 9 a.m. My name is Gabe Grand. I am a PhD student at MIT with a research interest in program synthesis. And I will be introducing our two speakers. So our first speaker is Caleb Stanford. Caleb is an incoming professor at UC Davis and is currently doing his postdoc at UCSD. And Caleb is going to be telling us about logic and decidability.
All right. Yeah, all right. Thanks, everyone, for attending this session preview for Logic and Decidability 2, which will be tomorrow. So it turns out that everything in PL is really just logic. Whether you care about types, assertions, or programs, all of those can just be encoded using formal logic. And more for PL researchers specifically, whatever your favorite program property is that you're interested in studying, it might be useful to take that property and encode it using some fancy new logic. There are many advantages of doing this, but for example, two of them are it allows you to gauge the expressiveness of the properties that you care about. So in kind of a more objective way, there's a lot of different formalisms out there. It's kind of hard to compare, but logic is kind of very standardized, so you know exactly how expressive it is. And second, you might just be able to outsource verification of your properties to some tool that somebody else wrote, and that's great. So you're going to take your fancy logic, send your formulas over to Z3, and hopefully we're done, right? You've solved your problem. Unfortunately, no, because of undecidability. So the more expressive your logic is, the more likely it is that you'll kind of venture into terrain that existing tools just don't really know how to solve. So kind of at the bottom, we have the world of SAT solvers where everything is decidable, and then the more and more expressive you go, you get up to SMT solvers where some things are undecidable, and proof assistants where basically everything is undecidable. And so a lot of work in logic specific for a PL audience is generally about exploring this boundary between decidability and undecidability. So we want to take decidable results, extend them to greater sets of problems, more expressive logics, and bring some of those decidability results so that we can outsource more problems. So that's kind of the general motivation. So what is this logic thing? Quick logic crash course. So a logic consists of three components. So a logic consists of a syntax, which is kind of the logical operators. These are things that you can apply to Boolean operations and or not, equality, and then usually quantifiers. Second, you have a signature, and this is domain-specific symbols. So if I care about integers, for example, I'll have symbols for addition, multiplication, 0, 1, and the successor operation. And then finally, I need some set of axioms that will tell me what the things in my signature mean. So if I care about integers again, I might say something like, well, for all x, for all integers x, for all integers y, x plus the successor of y should be equal to the successor of x plus y. So that's a logic. It's those three components. And if we care about decidability and we want to extend decidability results to greater logics, more expressive logics, there are basically three things we can do. So if we have an undecidable logic, what do we do? We can restrict one of these three components. So either we're going to restrict the syntax by maybe limiting the types of logical operations that you can do. We're going to restrict the signature by limiting what symbols are available. Or we're going to add or remove axioms. And that can also affect the decidability. And this is basically the game that all kind of automated verification tools play, like Z3 and SMT lib standard. They're all just playing this game of how much can we restrict the logic how little can we restrict the logic to get it to be decidable. And this is particularly what the first two papers in the session will be about, is kind of extending decidability to more expressive logics. So with that, let's jump into the papers. So first paper is about theories of arithmetic. And theories of arithmetic go back to Hilbert's 10th problem. So Hilbert, in 1900, made this famous list of really, really difficult, unsolvable problems at the time. And one of them was this problem of deciding Diophantine integer equations. So these are expressions that look like this, or formulas that look like this, where you have a plus 3abc minus adef is equal to 0. And I want to know is there a particular choice of integers A, B, C, and D, E, and F, such that this formula is true? And it turns out this is undecidable due to much later Robinson and others proving this in the late 20th century. On the other hand, there are arithmetic theories that are decidable, but not very expressive. So, for example, if you restrict everything to be linear, so this is like the linear fragment of real or integer arithmetic, you get something that looks like this. So maybe I have 3a plus 4b minus 8c is equal to 5, and also a plus b is less than or equal to 4. And you'll notice that there's no general multiplication. There's only multiplication by constants. And this makes the whole theory decidable, which is great because we can automatically kind of resolve formulas in that theory. But it's not very expressive. So first paper is about extending that expressiveness to a greater, more interesting theory. And here the theory they focus on is something called the theory of linear real rings. So what we're going to do is generalize. We don't just have constant multiplication, but we have general ring multiplication. But then we have some interesting axioms that kind of restrict it, but don't restrict it all the way to undecidability. So in particular in the paper, there's this kind of fascinating axiom, which is saying that for all x, if 0 is less than or equal to the sum of x n times, then 0 is less than or equal to x. So it's kind of saying that positive numbers are still positive if you divide them by n. Anyway, there's a set of very interesting axioms that kind of manage to reach this sweet spot between decidability and undecidability. Okay, so a second paper looks at a very different fragment of first order logic that is also decidable. So let's start with horn clauses. So horn clauses show up a lot in SMT verification, and they're basically just if-then statements. So here's an example horn clause. I say if x equals 3 and y equals 3, then x plus y should equal 6. And I'm only allowed to use this if-then construction. So I can't use or not. And it turns out that the theory of horn clauses is still undecidable. So great, we restricted the syntax, but we're still undecidable. However, there's an even more restricted theory of horn clauses that turns out to be decidable, and that's a fragment called monadic shallow linear. And this actually encapsulates a lot of properties that come up in practice. So here's a bunch of examples from the paper that I thought was kind of nice. So all of these are examples of monadic shallow linear formulas or horn clauses. And you can see that they're encoding things like red-black trees, things like less than or equal to properties. And what makes them monadic shallow linear is at least the linear part, is this fact that you never have the same variable twice in the conclusion of a rule. So here we have less than or equal to xz, but we wouldn't be able to say less than or equal to xx. And this is decidable, so that's great. However, we still want to extend that to be even more expressive. So the second paper is about extending this to higher order logic. So if you go back to our kind of landscape of less expressive to more expressive logics, at the bottom, less expressive, we have propositional logic. Then we have first order logic with quantifier-free formulas. Then first order logic with general quantifiers. And then we have higher order logic. Those are kind of the hierarchy of four logics. And here, this is basically pushing us from first order logic up to higher order logic, while still retaining decidability. And then the last paper is about a change of gears. So for the last paper, we're going to go from logic to state machines. There's a very deep connection between logic and state machines or automata theory. For example, in the theory of strings, so string constraints are off, like here we have a string constraint that says that S is either January, February, or March, and then it kind of has a date which is between 0 and 30, or 1 and 30, something like this. And if you take this string constraint, you can encode it as a state machine. And this is widely used in a lot of verification procedures for the theory of strings. But state machines are also more generally useful in other theories as well. And one thing that we really, really care about in the theory of strings and in automata or in state machines is minimization. So once we've taken our string constraint, converted it to a state machine, we want to minimize that state machine by deleting things that are irrelevant and by merging states that can be merged so that we get the smallest state machine possible. And this turns out to be really important in order to have an efficient decision procedure for the logic in question. But unfortunately, we have to write specialized minimization procedures for every single type of state machine that you can think of. So that's not just DFAs and NFAs. It's also transition systems, Markov chains, probabilistic automata, weighted automata, all these different types of state machines. you're going to have to write a custom procedure. Well, there's some fun existing work that actually shows you can do it generally for all types of state machines at once, using this fancy like functor stuff, and you can compose these different functors, and you get basically a decision procedure for minimizing the state machine regardless of what type of state machine you have. So that's pretty cool. And it's actually really good asymptotic complexity as well. So it gives you O of m log n, where m is the number of edges and n is the number of states. However, it still turns out to be slow in practice. So this work is about a new minimization algorithm that actually ends up being fast in practice. And it's built on this really exciting tool called BOA, which is implemented in Rust and which you can try out. And seems to also beat a lot of very specialized tools despite being general to kind of this general functor scenario. So with that, quick advertisement. My group is hiring. I'm working on some things related to logic. And I'm hiring students. And I hope to see you tomorrow at 9 a.m.